The National Bank in Graftopolis has been robbed. The police department is just around the corner. Will the robber be able to escape from the cops? Or should he just give up and return the money? Surprisingly, there is some graph theory that could help in answering this question. In Graftopolis, everything is a simple connected graph. Locations are vertices and streets are edges. The rules of this pursuit are strict. The cop picks a starting spot, then the robber picks theirs. They take turns moving to an adjacent spot or staying put. Most importantly, both players have perfect information. They can see the whole map and each other's position at all times. Picking the initial position is also part of their strategy. So, for example, a robber will never choose to start at a vertex directly adjacent to the cop. Well, unless if they're forced to. If the cop can guarantee a catch in a finite number of moves, the city is a cop win graph. If the robber can run forever, it is a robber win graph.
The layout of the city changes everything. For example, in a complete graph where every single place is connected to every other place, the robber is toast, so the cop can catch them in exactly one move. Now let's consider a tree. A tree can be visualized as a city with no loops and only one unique path between any 2 points. Here, the cop has a clever strategy, which is always moving one step closer on that unique path. Since trees are finite, the robber will eventually run out of road and gets cornered. Now, what if Graftopolis is built like a cycle? By a cycle, we mean a big loop of 4 or more locations, since a loop of 3 locations will yield a complete graph. Here, the robber can just keep moving in the same direction as the cop forever. In this loop, the robber always has a way out, and this graph will always eventually lead to a robber win.
But what about more complicated graphs? Knowing whether a random graph is a cop win or a robber win is not that simple. In order for us to proceed, let's observe the state of the graph before the cop catches the robber. Definitely, the cop is at a vertex adjacent to the robber's vertex, and then they move to the next vertex to catch the robber. We also know that the robber must have tried to avoid this situation in their turn, so it must have been the case that all of their adjacent vertices were also adjacent to the cop. The robber would like to avoid being in such position. We define a pitfall as the vertex whose neighborhood, including the vertex itself, lie completely in another vertex's neighborhood. We will call that one the attack vertex.
So now we know that the cop is going to win if the robber's vertex is a pitfall. These are some pitfalls and attack vertices for the examples we covered earlier. Notice that the cycle, which is a robber win graph, has no pitfalls. A graph must have a pitfall to be a cop win graph. But the opposite is not necessarily true. For example, this graph has a pitfall, but the robber could still win by just avoiding to enter it. So, we know that removing a pitfall from the graph does not change the winner, as they could just play on the smaller graph. If the robber wins on the graph without the pitfall, then he does on the one with it. The same applies for the cop. So we could just keep removing pitfalls from a graph. If only one vertex remains, then it is a cop win, because clearly a one vertex graph is a cop win. The game is over before it really starts. If more than one remain, then it is robber win. But what if the graph is too complex for just one cop? Then we need more cops. The minimum number needed to win is called the cop number. But before we explore that, let's look at the isometric path lemma. Imagine a shortest path between 2 points in the graph. Let's call it path P. If a cop patrols this path, they can perfectly shadow the robber. Because it's the shortest route, the cop can match the robber step for step from a distance. If the robber ever tries to step onto path P, the cop will instantly catch them. So, just one cop can completely block off any shortest path.
Welcome to part 5. To prove 3 cops can capture a robber on any planar graph, we rely on the Jordan curve theorem. Simple closed loop strictly separates the plane into an inside and an outside. We use this to define the robber territory, the set of all vertices the robber can reach without running into our cops or crossing guarded paths. Our main strategy is to trap the robber by systematically shrinking this territory. We do this using 2 cases. In case A, the robber's territory is guarded by a single bottleneck U. By stationing our cops at U, the robber is cut off. We can then establish this as our new base, effectively removing U from the board and shrinking the graph. But what if the territory is bounded by a cycle of 2 paths? This is case B.
In the first subcase Pi, the robber's territory touches only one of the boundary passes through a single bottleneck vertex. Cop 3 simply steps in to guard that connecting bottleneck. Because there is only one entry point, this perfectly isolates the territory, turning us directly to the logic of case A. However, if the territory touches both boundary passes, we have case PIR. Here we find the shortest path Q that cuts directly through the territory from one boundary to the other. Our third cop steps in to guard path Q. By the Jordan-Krebs theorem, path Q splits the cycle into two distinct halves. The robber is forced into one side. Instantly bring up one of our cops, and we proceed by case P again. In every scenario, we successfully shrink the robber's territory by at least one vertex, while always keeping a cop free to move. By repeating this loop, the territory eventually vanishes and capture is mathematically guaranteed. 3 cops are always enough for planar graphs. Thank you for watching.